Konnichiwa. We stand right at the precipice of a completely silent revolution, and it's one built not of steel or steam, but of pure, relentless mathematics. A mind of math, a cold design, where hidden rules and data align. Today, we are going to unravel the profound mystery of exactly how lifeless numbers so convincingly mimic human intelligence, transforming the abstract into something incredibly capable. So what does it truly mean for a machine constructed entirely of mathematics to, actually learn? Well, picture a human toddler for a second. That child can spot a scrawny stray cat out on a fence and instantly recognize it simply from having seen a few family pets. No one handed them a biology textbook, right? Now contrast that with a computer. A computer has to process literally millions of images using pure mathematical parameters just to achieve that exact same recognition. How does it cross that massive chasm?
Section 1. The core learning loop. To really understand this loop, imagine you are trying to bake the absolute perfect chocolate chip cookie, but entirely without a recipe. You just slowly experiment, batch after batch, until you find that perfect balance. Well, that is the essence of machine learning, improving at a task through experience, without any explicit human programming. There is absolutely nothing magical or philosophical occurring here. It is certainly not conscious thought. Instead, it's a highly disciplined, repetitive loop of guessing, measuring, and adjusting, all executed at blistering speeds.
We can actually easily remember this process with the simple mnemonic DIGME. Data flows in, an initial guess is made, we get the error, we modify the parameters, and we end when the error is minimized. The algorithm always starts from absolute zero. Its very first attempt is completely random, and it relies heavily on the resulting error as an invaluable teacher. It's a tireless engine of trial and correction, inching ever closer to cold perfection. Let's look at exactly how that error is measured mathematically. Suppose the machine guesses a value of 0.2 for a cat image, but the true label is actually 1. Well, 1 minus 0.2 yields an error of 0.8. Now, this 0.8 is not a failure. Not at all. It is a highly precise instructor, dictating the exact mathematical correction required for the very next attempt. And this precise instruction relies on a fascinating process called backpropagation. Backpropagation is essentially the passing of that error backwards through the system, so every single parameter knows exactly how to improve. Just picture the delicate turning of billions, literally billions, of tiny internal knobs or weights. Over millions of repetitive cycles, which we call epochs, these tiny adjustments systematically shrink the error down to near zero. Section 2. Architecture of Deep Learning. Consider the deeply layered human process of reading. You don't just absorb a whole book at once, do you? You read individual letters, which form words, which then assemble into sentences. Deep learning functions incredibly similarly through something called automatic feature extraction. The mathematical functions progressively assemble basic components across deep hidden layers. Layer 1 might just detect simple edges. The next layer assembles those edges into curves and shapes. And finally, the deepest layers recognize complex objects, like the distinct point of a cat's ear. From pixel to picture, the patterns emerge as data and math systematically converge. Section 3. 4 paradigms of training. Now, the chosen training style depends entirely on one single critical factor: exactly how much guidance or data labeling is provided to the machine up front. We can cleanly map these out using the mnemonic SUSR: supervised, unsupervised, semi-supervised, and reinforcement learning. Each paradigm dictates whether answers are provided, how the system learns, and what specific tasks it is fundamentally best suited to perform. First, let's compare supervised versus unsupervised learning. Supervised learning is like a teacher using a strict answer key to grade spam filters. Every single piece of data has a clear label. Unsupervised learning, conversely, provides absolutely no answers. It is akin to a child independently sorting a massive mixed pile of Legos into natural clusters based purely on shape or color entirely without an instruction manual. Next up, we have semi-supervised versus reinforcement learning. Semi-supervised learning blends the two together. It's like a teacher carefully grading half the homework and then trusting the students to finish the remainder using those core principles. Reinforcement learning, however, is purely a game of trial and error. It trains game-playing AI and complex robots through rewards and penalties, very much like training a dog with treats and corrections. Section 4. When the machine fails. Of course, these mathematical frameworks are not without profound vulnerabilities. As the old rhythmic idiom wisely reminds us, a foundation of flaw leaves no room for doubt. Garbage in reliably guarantees garbage out. Poor data quality is always the most obvious culprit. But we also see overfitting, where the machine perfectly memorizes the training data, but then totally fails in the real world. Underfitting occurs when it just fails to learn at all. Furthermore, inheriting dangerous statistical bias from imbalanced data, or simply applying the wrong training approach, well, that can render the entire system entirely useless.
This overarching limitation is perfectly captured by the parrot analogy. Think about it. A parrot might learn to squawk a cheerful greeting when you enter a room, but it has no conscious understanding of what a morning actually is. Similarly, a machine is an extraordinarily talented pattern matcher, reacting strictly to pixel arrangements and statistical probabilities. It possesses absolutely zero genuine comprehension of the real world.
Section 5. Synthesizing the machine mind. As we synthesize the machine mind, we really must recognize the monumental scale of this invisible, tireless machinery. Let's solidify these core concepts one last time. Learning is an iterative loop easily remembered as DIGME. Deep learning stacks complex mathematical layers for automatic feature extraction. 4 core paradigms: supervised, unsupervised, semi-supervised, and reinforcement, or SUSR, expertly guide the training process. And above all else, we must remember, machines masterfully match patterns they do not genuinely understand. I want to sincerely thank you for investing your time and focus today. If you found real value in this, please like and subscribe, and make sure to click the bell icon for all our future uploads. I'd love it if you'd leave a comment below with your absolute favorite part of this analysis, where in the world you are watching from, what you would like to learn next, and any suggestions you have for improvement. I sincerely thank you for every single comment. I read them all. We began today by asking what it actually means for a machine to learn, and we have found our answer in the rigorous mathematics of pattern recognition. But this leaves us with a lingering, truly profound question. If these systems only mimic understanding, what happens when we inevitably trust them with our most profoundly human decisions?